Hello everyone, in this video we're going to pick up where we left off in section 13.2 with example 2. So what we had talked about in the last video was if I looked at the limit of the numerator, it equaled 0, and if I looked at the limit as y approached 0, 0, the denominator, it equaled to 0. So we can't just take the quotient of the limits. So what we need to do is we need to use the definition of a limit, right? That epsilon delta definition of a limit. Okay, so before we can use that, we need to have an idea of what the limit is, right? And so the idea is as x and y values are approaching 0, 0, right? In other words, think about this is the plane, right? If the x and y plane is the flat surface there. So as I'm approaching 0, 0 from every single direction, right, as I'm approaching this point, which is 0, 0, and then whatever the y value, or I'm sorry, whatever the z value is, whatever height is L, whatever the limit should be, right? And it looks like that no matter what angle I'm coming in from that flat plane there that slices it right in half, the xy plane, it looks like, again, you can't really tell from this angle, but it looks like that this limit is 0, right? In other words, I'm heading to 0. So I actually have a nice 3D drawing of this, or a 3D graphic of this graph. And as you can see here, the x and y plane is the plane that's made by the green and blue. I'm sorry, the green and red, right? And the z-axis is the blue. All right, so no matter which way I turn this, if I look at points along the plane, the white plane there, if I'm on that white plane heading towards the origin, it looks like no matter what direction I'm coming from, the graph is always heading toward the origin. In other words, it's heading towards the z value equal to 0. Right? Even if I'm coming up this hill, or even if coming maybe down this hill, I'm still heading to the z value equal to 0. Right? So that's our intuition as to why we are going to say, hey, we think that limit is 0. Let's use the limit definition to prove that. Right? So from the graph, it looks like the limit is L equal to 0. So that's what we're going to use in our limit definition, right? So what I'm going to do is go ahead and copy this thing here because we're going to use it. Whoops, not cut. We're going to use it over and over again. Well, we'll use it and we'll talk about it here. Okay, so remember the idea here is that the key here is that there existed delta for each epsilon. So what we're going to do is we're going to do some side work and say to figure out what delta is, and then once we find that delta, we'll show that it holds, and then that means that the limit exists, right? So this is going to be side work to find delta, right? That's how these proofs work to figure out what the limit is. Okay, so first we need to notice two things. And off the top of your head, you'll be like, what? But we notice them because this obviously is the book helping us how to do this. But if we were to go through the proof or the ideas, we get to this point and we'd be like, what? And then we think of these ideas. So we're just thinking of them ahead of time for the sake of making things go smoother. But if you're doing one of these problems by yourself, you do all this work and you get to a point you're like, oh, what do I do now? And then you'd use a fact, so you'd have to find one of these two facts that I'm about to show you. Okay, so the facts that we need in this case is that the absolute value of y is less than or equal to x squared plus y squared underneath the square root. Okay, and then the second thing we need, so I think we might have to shove things down a little bit. So that's the first thing we need, and then I'll put it over here. The second thing we need is that x squared over x squared plus y squared is less than or equal to 1, right? So why is this one true? Because of the triangle inequality, right? And then why is this one true? Well, think about it. The denominator, I know that if it was x squared over x squared, it'd be equal to 1, right? But it's not. We're adding y squared in the denominator. So we're adding something in the denominator. So that makes the denominator a little bit bigger than just x squared. So that makes the whole thing a little bit less than 1. Right? So we have these two facts here that we needed to notice. And I'm going to highlight these facts. Maybe I'll highlight it in blue, fact 1, and then we'll highlight in green, fact 2. Right? So blue we'll do here, and green we'll do here. Okay. So in a delta neighborhood, again, we don't know what delta is. We're going to find out what delta is. But say I did know what delta was, or say we just called delta equal to delta. Again, we don't know delta yet. About which point are we focusing on? What point are we heading towards? The point that we're focused on here is the point 0, 0. So in some delta neighborhood about 0, 0, what do we have happen? We know that we have this happen, right? Because it's saying if that. We want to show that if we have this, then we have this. So let's assume that we have the purple thing, right? So in a delta neighborhood about that, we know that 0, because what is a delta neighborhood? It means that if I take some point x minus whatever point we're focused on, in this case, we're focused on x not equals to 0 and y not equals 0, but let's write it in general. So y squared, right? But in our case, what is x not y not? Well, this is 0 and this is 0, right? So here I get that x squared plus y squared is less than delta, right? Because it's a delta neighborhood, so I know that the distance between any 2 points, or I'm sorry, any point in that neighborhood is less than delta, right? The distance between any point x, y and 0, 0 is less than delta, right? So in a delta neighborhood, this is what we have happen. Okay, and I'm going to go ahead and highlight this in a different color because we're going to need this fact as well, that x squared plus y squared underneath the square root is less than delta. Okay, let's move this down a little bit. So we've got 3 facts so far. Then, so if we have that, then if I looked at, now we look at the second piece, right? The second piece is this piece down here, right? So that piece, I'm going to look at f of x, y, which is my function, minus my limit. Well, what is my function? In this case, my function is 5x squared over y, or I'm sorry, times y over x squared plus y squared. And then what is the limit? The limit's 0, right? So this is equal to just 5x squared y over top of x squared plus y squared in the absolute value. Okay, so now we have to play some games. So here, notice x squared is greater than or equal to 0. 5 is greater than or equal to 0. X squared, again, is greater than or equal to 0 because it's something squared. It can be negative. And y squared is all greater than or equal to 0. So in other words, that absolute value is redundant for everything that's already positive. So the only thing that's really benefiting from the absolute value is the y, right? So I know I can rewrite this as 5 times x squared over x squared plus y squared times the absolute value of y. Right? Because this stuff, writing the absolute value around that is redundant. Okay. So now I can have some fun. And this is where I said if you were doing this proof by yourself, you get to this point and you'd be like, I need to know something about this, and I need to know something about this, right? But what do you know? That's fact 1 and 2, right? So by fact 1, I know that this guy, y, I can maybe write it in blue here. This guy is less than or equal to the square root of x squared plus y squared by fact 1. And by fact 2, which again I'll maybe write it in green, I know that this guy is less than or equal to 1, right? So what I'm going to do is write a less than or equal to sign here and write 5, because we don't know where 5 is just 5, and I can replace this big old thing with 1 because I put less than or equal to, and I can replace the other thing, the absolute value of y, with the square root of x squared plus y squared, right? But now, what is x squared plus y squared underneath the square root less than? If I looked at 3, this guy right here, the third thing I highlighted, this guy is less than delta, right? So I can replace this less than or equal to with just a strictly less than, and then 5 gets left alone. 1 is just 1, so I forget about it. And then now instead of writing the square root of x squared plus y squared, I can write delta, right? And remember, what was our goal? Our goal was to say, okay, if I'm in this neighborhood, cool, then this whole thing right here is less than epsilon, right? So in the back of my mind, I wanted that less than epsilon, right? So if I let delta, right, because I know this whole thing is less than 5 delta. If I let delta, I guess I can put it right here. I'll put it right here. Let delta equal to epsilon over 5. If I have that happen, then when I get to this point, I can say, okay, this is 5, and then instead of delta, I can write epsilon over 5. The 5s will cancel out, and I'm left with epsilon, and it'll be less than epsilon, and I'll be in good shape, right? So I did all this work to figure out that this is what delta should be. Because remember, the whole point was saying, for any epsilon, I find a delta, such that if this happens, then this happens. So now that's what we're going to do. We're going to finish the proof. The idea is to kind of write out this whole definition and show that it holds in this case where we let delta equal to 0. I'm sorry, where we let delta equal to epsilon over 5. Okay, so let epsilon be greater than 0. Then there exists delta equal to epsilon over 5 such that if, what do we have happen? If 0 is less than, well, here's our definition, right? The purple thing. If 0 is less than that, blah, blah, blah. But what's our point? Our point is x naught, y naught equal to 0. So such that the distance between any point x, y, and 0, 0, in other words, the square root of x squared plus y squared, is less than delta, which now in this case is, we said delta is equal to epsilon over 5, right? Then, what we say our limit was, we said our limit was going to be 0, right? We thought our limit was 0. So I can say then f of xy minus 0, which we already kind of did a lot of this work. It'll be a little bit redundant, but what is f of xy? F of x squared y over x squared plus y squared minus 0. So again, what is this? We said that this was less than or equal to, if we follow all this work here, it's less than or equal to 5 times the square root of x squared plus y squared, again by all this work down here, or up there. But what is x squared plus y squared underneath the square root? That's less than delta, which is equal to epsilon over 5, so I can say less than 5, and then epsilon over 5, but epsilon over 5 times 5 is epsilon, right? So what did we show? We said let epsilon be greater than or equal to 0, then there exists a delta. here's our delta, such that if I lie in an epsilon if I lie in a delta neighborhood where delta equals epsilon over 5, then the difference between my guy and my limit is less than epsilon. So what did we just show? We just showed that the limit is equal to 0, right? Therefore, the limit from every direction, which we denote by the limit as y approaches our guy 0, 0, of 5x squared y over x squared plus y squared is in fact equal to 0. Right? But we had to show all of this work to show it thoroughly, that because this takes care of from every single direction, right? Because remember, in the x and y plane, this is the point 0, 0, and we wanted to approach it, say this is x, y, we wanted to approach it from every single direction, right? And so this epsilon delta proof that we just did shows every direction, and we're good to go. The limit is equal to 0. All right, that's all for this video. Thank you.